So I'm going to talk about the visualization of population of orbitals. And first of all, we need to create our input files, and these are the input files that we need for non-adiabatic dynamics, and that is the RRR file, that is the output of the correlation code, and the energy pop file that we use for the geometry optimization calculation, and the master equation that is in the format of OS strength, that is the OS strength file in the matrix format, and then the band out file, that is the integration of per charge files, and this MATLAB code that we use for the charge carrier dynamics, and this is the location of MATLAB code. So for creating the master equation, we move towards the into the geometry optimization folder, and then we will create the input overlap file that we already have, and then we use this command to create the master equation, and then we convert this master equation into the master optics, and it will be in the format of this matrix as this figure has. And then the band out file, for the band out file we create the folder and copy content from the geometry optimization, and then we use the postcard file from the previous geometry optimized card file, and then we modify the in-car file, the number of bands and the energy energy intervals, and then we run the wasp, and after when we have the per charge files, then we use this Perl script. We need to modify, we can take the script from this directory, and then we need to modify the line 6 of the script, in which we need to provide the information between the number of operators that we are going to use, and then we run the Perl script, and we got all these files we got all the background file in that, and the results can be shown in this figure. So after that we have the files, and we can transfer these files into the same directory at our local computer, in which we have the MATLAB code, and then we need to edit the input parameters in the MATLAB code that are explained by many previous speakers, and then we need to run the MATLAB code. And so this is the figure, that is the output of this MATLAB code, and which gives us the information with time step how the electron move from the HOMO into the LOMO, and their difference in their energy. And the green area shows the normal distribution of electron and holes. That's it from my side.
Okay, please join me in thanking Amara. So, any questions in the room? Any questions on the line? Any questions in the chat line? So, Amara, there is a question in the chat line. Will you please read and answer?
Yes, sure. Is the matrix optic file a matrix? Yes, this file is in the form of matrix, like this matrix.
Okay, good.
It's not a matrix. The MATLAB code converts it to a matrix. It's just a line.
Okay.
It's not a big deal. It's just you mentioned it.
Okay.
Amar, would you please go to the last slide?
Yes.
So, would you please? Well, we plan to speak on the following subject again next week, but your diagram shows K sub E and K sub H. Would you share your opinion of what this notation stands for?
I'm not sure about it, but
Do not give exact answer. Just your impression, feeling. How do you interpret the figure? Like, what are these notations? What they point to? Just try to analyze as we go.
this can be the electron.
That's what you see by looking at the figure. Where the vertical line labeled as KE crosses the dashed line, dashed yellow line. At the beginning, at the end, or in the middle?
In the middle.
And how do you see, is it at the beginning of the middle or at the end of the middle or in the center of the middle?
In the center of the middle.
So just try to analyze try to give any suggestions, how can it be interpreted?
It can be when with the time step the electron
Yes.
energy decrease.
Exactly. So it specifies average rate of energy relaxation. Yes, perfect.
Okay.
Does everyone likes it, or there are more additional details how to tell it in different words? Yeah, it's good. It's good. Okay, more questions to Amara. Questions 1, questions 2, questions 3. Let's thank Amara once again.